Okay, good morning, friends. Last lecture we discussed about the pin configuration of 8086, how to operate the 8086 in a minimum mode and maximum mode, what are the status signals and control signals supported in a minimum mode and maximum mode, and many co-processors such as 8288 and 8286. These are the co-processors, bus controller and the transceiver dedicated ICs, and how to connect with the microprocessor. So that we have discussed in the last lectures. So now let us discuss one more co-processor called as 8087. So 8087 designed and developed by Intel. It is also called as a math co-processor, and NDP means numerical data processor. So NDP or math co-processor, you can call it as a 8087 co-processor. So why we required this 8087 co-processor or math co-processor? Many mathematical operations which are complex in nature, we require to perform lot of mathematical calculations for engineering applications in business, graphics. They require lot of complex mathematical calculations such as log, then arithmetic operations on very large numbers, also operations on very small numbers. So to perform these mathematical calculations which are complex in nature, the 8086 is not sufficient or inefficient because it is busy in general. It is called a general purpose processor, the 8086. It can't perform this type of large mathematical calculations. We can perform the mathematical calculations which are complex in nature by writing in high level languages such as C, C++, Fortran, or you can write the mathematical calculation through assembly language also, but it is also time consuming. And if you write the program in high level language, we require the link compile, which makes the total operation slower. The another method is to buy the library of the floating point arithmetic from the manufacturers, where I have already discussed about the procedures. Through the procedures, we can call and return the operations which are present in a library. So we have to purchase the library from the manufacturers. In that library we have everything, all the mathematical models. We have to call it from the procedure and return it. So this is one of the methods. There you can see here 1, 2, 3 different methods. So these what we see are different methods, but all has some drawbacks. Like in the high level language we require the compiler. In assembly language we require the assemblers. We have to link the object file with the source. These makes the time consuming. And the third method, what I told as a library, purchasing of the library, that also we require the procedures. So these have some disadvantages or drawbacks. For a dedicated mathematical operations to perform, Intel developed a dedicated math coprocessor This is designed to perform very complex mathematical operations. So that is very quick. But 8086 is not a quick as a 8087. It takes a lot of time to perform the mathematical operations. So 8087 is a very fast and it is dedicated mathematical coprocessor. It is designed to perform very complex mathematical arithmetic and operations. So it is 100 times faster than 8086. You can see here it is 100 times faster than 8086. 8087 has its own specialized instruction set that we're going to discuss. By discussing about the instruction set, they are the specialized 8087 instruction set. The 8086 we have to connect with the 8087. The 8086 is used to perform the general operations such as fetch, decode and execution. The 8086 connected with the 8087 in parallel. Okay, so the fetch and decode perform in parallel operation and the instructions are stored in a queue. Already we know what is the queue. So all the instructions are stored in a queue. So the instructions of 8086 and instructions of 8087 both are present in a queue. The instruction, if it is belongs to the 8087, the 8086 have to neglect that instructions which is belong to the 8087. So in that case it will go to the NOP, means no operation. If after decoding, already we know we have the three operations performed by the CPU: fetch, decode and execution. After fetching, it will have to be decoded. While decoding, if the instruction belongs to the 8086, then that instruction is considered by the 8087 as a NOP, means it will not perform any operation of that instruction because that instruction belongs to the 8086 and vice versa. If the instruction belongs to the 8087, the 8086 goes into NOP, means no operation, or it will send that instruction to the 8087. So that is one of the how to distinguish the instructions in the queue for the 8086 and 8087. That here you can see NOP. Already we have seen the use of the NOP. It is used in a delay program to generate the delays. Okay, so let us see what are the different instructions of the 8086 and 8087. How to distinguish or how to recognize after decoding the instructions are belong to the 8087. That is by prefix 11011. So that here you can see if the instructions in a MS bit, most significant bits of the instruction consist of 11011, then that instructions belongs to the 8087. How to distinguish or how to recognize? All the instructions of the 8087 in the MS bits, it consists of 11011. Okay, so that you have to remember. And the instructions of 8086, we don't have the MS bits of this 11011. Keep in mind the instructions of the 8087 in MS bit we have 11011, that distinguish with the instruction of 8086. We have the common queue, so that in that queue we have the instructions present for both 8086 as well as 8087. Okay, so let us see what are the data types supported by 8087. There are three data types: binary integers, fact, decimal, real numbers. So let us see one by one what are the data types they are supported. The binary integers, that is the first one, again divided into three types called as binary integer, then word integer, and binary integer, word integer, and short integer. So there are three integers belongs to the binary. So word integer, short integer, and long integer based upon the size of the numbers supported by the integers. So let us see the word integer. This is the figure. You can see here this figure. So 0 to here 15 is a range for the binary integers. The MSB, this one, the last 15 digit called as MSB. It has the sign. To represent the sign, you have the sign bit in a MSB, that is 15 digit, 0 bit, that is LSB. So 0 to 14, you have the magnitude. Here you can see the M. This is the M which represents the magnitude, and last is belongs to the sign which is used to represent the number of positive or negative. That is called as a word integer. So in a word means it is a 16 bit. So positive numbers in a MSB, the means 15 digit. If you have the 0, then it is a positive number. In a MSB, that is 15 digit. If you have the 1, then it is a negative number. So how to represent the numbers, positive and negative number? If the MSB here is 0, then it is a positive number. If the MSB here 1, then it is a negative number. The negative number is represented in a 2's complement. Already we know the negative numbers that are represented in 2's complement representation. That is in this word integer. Always the lower byte stores in a lower address of memory. Lower bytes means 0 to, starting from 0 to 15. The lower bytes will be stored from lower addresses of memory. Okay. Next, let us see the short. Next, let us see the range supported by the word integer. You can see here minus 32768 less than and equal to plus 32767. So negative numbers in a word integer starting from minus 32,768 to plus 32,767. So the minus to plus, these are the negative number range supported by the word integer. And positive numbers 35,536. Already we know it is a 16 bit. So starting from 0 to 65,536, all are positive numbers above 0. So 65,536 is a range for positive numbers and negative numbers. Let us see the second one, short integer. So it is, the range is from 0 to 31, and the last 31 bit already told is a MSB. So this MSB is used to represent the positive number or negative number, and the range is from minus 2 10 to the power of 9 to 2 to the power of 10 to the power of 9, minus 2 to plus 2 10 to the power of 9. That is the range supported by short integer. Let us come to the long integer. You can see the range instead of 0 to 31, now it is supporting from 0 to 64. Okay, so it is a 32 bit, it is a 64 bit. Okay, so the range is from minus 9 10 to the power of 18 to plus 9 10 to the power of 18. That is a range supported by long integer. So these are the numbers you can see we can perform in this range of numbers the mathematical operation. That is the advantage of 8087 or numerical data processor. Next, let us see the second type of data type called the packed decimal. The packed decimal range is from 0 to 79. 0 to 79 is the range for the packed decimal. Here you can see, and the range is from minus 99 to plus 99. So these packed decimal numbers widely used for a financial application, and number as much as 18-bit wide we can use by packed decimal. So let us come to the third data type of 8087, that is the real numbers. The real number again divided into three types: short real, long real, temporary real. So in short real means the numbers which support the decimal point. These numbers are also called as a floating point numbers, which consist of integer and fractional part. We have the integer part and fractional part. Example is 9.4. Such numbers are called as a real number. So real numbers, there are three types: short real, long real, temporary real. So refer this figure, the figure here. This shows all the data types. Here you can see the 1, 2, 3. These are the integer types: word, short, long. Then it is a packed decimal. You can see here one X, that is a do not care, and the range is from minus 99, you can see, to plus 99. Up to 18 digit we can represent by the packed decimal. Then you have the short real. So 0 to 32, 0 to 31. The S is a, here you can see this as a sign. Then we have the biased exponent. These real numbers are required when we multiply many real numbers where the floating point may change. It is not a fixed floating point or decimal point, fractional point. It will shift after any mathematical operation. In that case, we require this type of real numbers. So biased exponent is here. Okay, and next we have the significant numbers. So here you can see the different real numbers. Short real 0 to 31. It supports the range. Here you can see 0, 1, 2, 10 to the power of minus 38, 3, 4, 10 to the power of plus 38. So these are the range. And in the long real you can see 0 to 3, 10 to the power of minus 308 here, and 1, 7, 10 to the power of plus 308. So this much of range supported by long real. Temporary real 0 to, here you can see temporary real starting from 0 to 79, means it is a total is a 8-bit. It is a 8-bit wide. So that you can see here. 8-bit bank 0 to 79 means it makes total 80-bit wide temporarily real number. So that here see here 0 to 79, and the range is 034 10 to the power of minus 4932 to 1.1 into 10 to the power of plus 4932. So you can see here this much of range is supported by the temporarily real. Okay, these are the data types we have discussed. So let us see the architecture of the 8087. So 8087 architecture divided into two parts. So for this you can refer this figure. Here you can see the 8087 architecture. It is divided into two parts: control unit and numeric execution unit, NEU. Control unit and numerical execution unit, these are the two parts. Consist of a 0 to, here you can see 80-bit stack register, 80-bit wide stack register, and we have total 8 registers starting from 0 to 7. Then here we have exponential bus, fractional bus, programmable shifter, arithmetic model, temporary register, a tag word, operands queue, then microcode control unit, exponential model. Then we have a interface here which makes the interface between the two. So this is the architecture of 8087. We are connecting with this with the 8086. So let us see the detail. In a control unit we have the control word, here you can see, and status word, data buffer, operand queue, addressing, bus tracking, expansion pointers. So we have here status, here we have the status and address. So this is the architecture of the 8087. So let us see what is the control word. It is made up of control word and so refer this figure. Let us see what is the control word. The control word of 8087, by writing them to a memory location, 8087 executes an instruction which reads control word from memory. To read the status word from 8087, we require the status word, which is used to write the status word to memory. Here you can see we have the stack. The stack already we discussed, it is similar to the 8086. It operates in LIFO, last in first out. Here this is the stack operate in a last in first out method. It is similar to the operation of the 8086, where we have there are two operations called the push and pop. In 8087 it has 3-bit pointer which holds the number of registers as current top of stack. So top of stack is here, is represented by the 3-bit pointer. 8087, when it is initialized, the stack pointer points to the 0, 0, 0, and the register 0 is top of stack. These are the registers starting from 0 to 7, and the 3-bit pointer called the SP points to the 0, 0, 0, and the register 0 is the top of stack. Means register 0 is selected when 8087 initialized. The 8087 converts the number of memory to 80-bit temporary real format, and it decrements the stack pointer to 1, 1, 1, and writes the temporary real number to 1, 1, 1, and that is nothing but the register 7. Here you can see the register 0 is here and register 7 is here. When it is decremented, the 0 move to the 7. So that is a top of stack, means TOS. And so that is explained here, the operation of the stacks for the push and pop. You can see the first figure for initial position. The stack is on 0th position. Here you can see ST for the initial position, and the numbers are 3-bit from 0, 0, 0 to 1, 1, 1. So that you can see in the stack. In the stack we have the push and pop operations. That push and pop operations are explained here. For one push or one pop operation, the stack pointer will be decremented. The first figure shows after the reset. Here it will be 0, 0, 0 is a first register 0. For each push, here you can see the ST0. For each first push, the top of the stack ST is 0. Means the 0, 0, 0 for after first push, it will come to the 111. Means 0, this is 0th register and this is the 7th register. It will come to the 7th for first push. And second, you can see here in second figure, for 3 push, for the 3 push operations, here you can see X, X, X. So here you can see 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. So for 3 pushes, you can see it is initialized the TOS here. So the ST0, ST1, ST2. So for 3 pushes, the top of stack is ST0. That is shown in a circular fashion. It is operating in the stack of a 8087. Okay. Then let us see the control board register. Here you can see the control word register. This is the status word register of the 8087. So control register and status register, you can go through it. These are the register help for the 8087 operations. Next, coming to the 8087 instruction set. So the mnemonic starts with F when stands for floating point and also distinguish from 8086 instructions. The mnemonics of 8087 always start with F, which stands for F nothing but a floating point, and also it is used to distinguish the 8086 instructions. Calculation is very fast. For a multiplication of two 64-bit real numbers, it takes the 27 microseconds. To perform square root, it will take 35 microseconds. So let us take some examples, the instructions of the 8087. Here you can see FINIT. So here you can see F prefix with the instruction. This instruction belongs to the 8087. So that means floating point initialization. So second instruction is a FLD, means floating point load. Floating point load. And third instruction you can see FMUL. Here. So FMUL means floating point multiplication. This F, you can see the difference between the MUL is a simple instruction supported by the unsigned multiplication of 8086, but here you can see the FMUL. So MUL and F. This F is the instruction belongs to the 8087. Next you can see FDPI, means it is used to load the pi 3.142. That value will be loaded if you use the instruction FDPI, this one. Then FST means store real number. Then to perform the floating point division, the instruction is a FDIV. We have used the DIV. DIV is a instruction of the 8086. If you have the F, then it is this instruction belongs to the 8087. Okay. Now these are some of the instructions we have seen for the 8087. Let us see an example for the 8087. A example which is used to find the square root and the circumference area, not the square root. This code belongs to the finding of area, circumference, radius. Okay, let us see the example. The example here you can see. The example here you can see data segment. This is the instruction of the 8086. ORG is also the 8086. The 8086 used to fetch. All the instructions are used by 8086 and 8087 are fetched by 8086. So ORG you can see that is the instruction belongs to the 8086. Radius, my number, area, circumference, DD, that is all are variables. Data ends here you can see. Then code segment. Then we have the code segment, that is also the 8086. Assume move AS, data, move DS, AS. Now coming to this FINIT, this instruction here you can see. This F means this is the instruction belongs to the 8087. So F then floating point initialization, then FLLD is taken here, given the FLD, that is the radius, load the floating point radius, FMUL, so multiplication of the floating point number here, FDPI means load the pi value, FMUL means multiplication, performs the multiplication on the floating point numbers, FST means store the floating point number of area, and FDU, that is the floating point number of radius. So this example shows the a code for the use of the instructions which belongs to both. Here you can see in this example, you have the both numbers, both instructions of both instructions belongs to the 8086 as well as 8087. So F radius, then FD radius, FLD load, FLD means floating point load, FMUL means multiplication of the floating point, FST means store the number, floating point number of circumference, F weight means weight of the, still the result will be displayed. It is used to halt the operation of 8087 by F weight. So this is the example for the instructions belongs to 8087. Here in this example you can see we have used both the instructions of 8086 and 8087. Okay, this completes the 8087 architecture, the control word, status word, how the stack, the 80-bit stack operates, the data type supported, and the range of the different data types, and the instructions you have seen here, and finally you have seen an example, the use of the instructions of the 8087. Okay, thank you.